Step into the captivating realm of Sci-Vid, where the intricate tapestry of scientific wonders unfolds before your eyes. In this immersive journey, we plunge deep into the mesmerizing labyrinth of quantum mechanics, navigating the elusive landscape of wave-particle duality. Accompany us as we decipher the enigmatic codes that govern the behaviors of particles on the quantum scale. Venture into the core of the dual nature of matter, a mind-bending concept that challenges the very fabric of our comprehension of reality. Seize the opportunity to become part of this intellectual odyssey. Subscribe now, activate the notification bell, and let's collectively unravel the cryptic secrets concealed within the quantum world. In the enigmatic realm of quantum physics, subatomic entities like electrons and photons display a perplexing dual nature, embodying both wave-like and particle-like characteristics. This captivating duality constitutes a foundational element of quantum mechanics, challenging the conventional understanding rooted in classical intuition. Historically, particles were conceived as discrete entities with precisely defined attributes, such as position and momentum. Conversely, waves were perceived as continuous disturbances propagating through a medium, akin to sound waves through air or undulating water waves in the vast ocean. Quantum mechanics disrupts this classical dichotomy, asserting that particles, at their smallest scales, can manifest wave-like behaviors. This is discernible in phenomena like diffraction and interference patterns, initially associated with the realm of waves. The iconic double-slit experiment epitomizes this duality, where particles, when passing through two slits, generate an interference pattern on the screen behind them, resembling the behavior of waves. Yet, under observation, they adopt particle-like attributes, aligning at specific points on the screen. Conversely, particles also showcase distinctly particle-like traits, possessing well-defined positions upon measurement, and describable properties in terms of discrete values. This wave-particle duality, challenging the classical perception of waves and particles as distinct entities, is a paradoxical hallmark of quantum mechanics. To navigate this surreal landscape, scientists employ mathematical tools like wave functions and probability amplitudes to elucidate particle behavior in the quantum domain. While these tools enable predictions regarding the probability of finding a particle in a particular state, they fall short of providing a comprehensive depiction of the particle's whereabouts before measurement. Essentially, quantum mechanics introduces a probabilistic dimension to particle behavior, where our capacity to precisely ascertain both the position and momentum of a particle is bounded by Heisenberg's uncertainty principle. Thus, comprehending wave-particle duality necessitates embracing a paradigm shift from classical determinism to the probabilistic and dualistic nature characterizing particles in the quantum realm. Wave-particle duality emerges as a pivotal concept in quantum mechanics, challenging the classical comprehension of particles. Historically, electrons and photons were envisioned as minuscule, solid entities with definite positions and trajectories. However, experiments in the early 20th century, notably the double-slit experiment, unveiled a confounding behavior. In the double-slit experiment, particles directed at a barrier with two openings create an interference pattern on the screen behind the barrier, resembling waves. This occurrence implies that particles possess wave-like properties, exhibiting the capacity to interfere with themselves. Yet, under observation, the particles manifest as discrete entities, forming a pattern indicative of individual impacts on the screen. This dual manifestation of wave and particle behavior extends beyond light, it encompasses all quantum particles. Wave-particle duality challenges classical intuition by suggesting that particles lack fixed attributes until subjected to measurement. Pre-measurement, they exist in a superposition of states, behaving akin to waves. The act of measurement subsequently collapses the wave function, determining the specific state of the particle. The Schrödinger equation furnishes the mathematical framework to elucidate this duality, offering the probability distribution of locating a particle in a particular state. This inherent probabilistic nature stands as a distinctive feature of quantum mechanics, underscoring the inherent uncertainty at the quantum level. Wave-particle duality accentuates the non-intuitive facets of quantum physics, demanding a probabilistic comprehension of particle behavior at the quantum level. It persists as a central tenet of quantum mechanics, perpetually captivating the attention of scientists and philosophers alike as they grapple with the ramifications of a reality where particles can manifest both wave and particle characteristics contingent upon observation or measurement. In the obscure domain of quantum mechanics, particles unveil a dual nature that oscillates between wave-like expansiveness and particle-like localization, a dance perceptible when unobserved. This enigmatic behavior is epitomized by the renowned double-slit experiment, where particles, in the absence of scrutiny, orchestrate an interference spectacle akin to waves. However, when subjected to observation, their demeanor morphs into that of discernible particles, tracing a pattern synonymous with isolated impacts. The very act of observation, it seems, wields an influence over the conduct of these particles. This dual existence, encapsulated in wave-particle duality, constitutes a linchpin in quantum theory, challenging classical convictions about the precisely defined attributes of particles. It accentuates the innate probabilistic and indeterminate essence of quantum systems, pushing against our conventional understanding of particle properties. Picture, if you will, a particle, a mere wisp in the cosmic fabric, assuming the role of a wave. Rather than adhering to a well-defined spatial position, this infinitesimal entity extends itself across the expanse like ripples on a serene pond. Its core diffuses, weaving an intricate tapestry of probability through overlapping self-interference. Yet, in the blink of cosmic time, this mystifying particle undergoes a metamorphosis. It abandons its undulating dance and materializes into a discernible entity. Visualize it now as a diminutive, localized object, a mere pinpoint in the vast cosmic tableau. It defies the fluidity inherent in its wave-like nature, opting for a precise location, as if the cosmos momentarily demands its singular, tangible manifestation. This dichotomy, this celestial ballet between wave and particle, thrusts a challenge upon the essence of our intuition, beckoning us to explore the mysterious frontiers where the infinitesimally small subverts classical comprehension. It invites contemplation of the profound and perplexing facets of quantum reality. The phenomenon elucidated finds resonance in the wave-particle duality intrinsic to quantum mechanics. In this quantum realm, particles such as electrons oscillate between exhibiting wave-like and particle-like behaviors contingent upon observation or measurement. This dual performance, akin to a cosmic ballet, transitions seamlessly based on the specific observational conditions, defying classical expectations of fixed properties. The probabilistic nature of their behavior renders their essence context-dependent, a departure from classical determinism. This inherent duality stands as one of the captivating and confounding aspects of quantum physics, prompting a re-evaluation of our understanding of reality at the quantum level. Scientists persist in their exploration of these phenomena, delving deeper into the fundamental principles governing the behavior of the universe's minutest building blocks. Let's journey back to the early 20th century, an era that witnessed a seismic shift in physics, courtesy of luminaries like Max Planck and Albert Einstein. This epoch laid the groundwork for quantum theory, introducing the perplexing notion of wave-particle duality. At the cusp of the 20th century, the prevailing conception of light and matter hinged on classical physics, portraying light as a continuous electromagnetic wave and matter as discrete particles. However, experimental observations began to challenge this classical paradigm. Max Planck, in the year 1900, propounded a revolutionary hypothesis to elucidate the spectral distribution of blackbody radiation. He posited the quantization of energy, suggesting that energy exists in discrete packets or quanta. This groundbreaking concept became the bedrock of quantum theory. Albert Einstein, building upon Planck's revolutionary framework, took a bold stride in 1905 by explicating the photoelectric effect. he advanced the notion that light comprises discrete energy packets called photons, each bearing a specific quantum of energy. This proposal further contested the classical wave theory of light. The revelation of wave-particle duality reached its zenith with the advent of the double-slit experiment. In 1927, Clinton Davison and Lester Germer demonstrated that electrons, conventionally perceived as particles, could manifest interference patterns akin to waves when traversing a double slit. This phenomenon, subsequently validated with other particles like photons, solidified the enigmatic nature of quantum entities. In the enigmatic realm of quantum mechanics, the wave-particle duality principle posits that entities, such as electrons and photons, possess the capacity to manifest both wave-like and particle-like attributes contingent on experimental conditions. Their conduct, characterized by probabilistic nuances, finds articulation through wave functions within the quantum mechanical domain. This duality not only challenges classical intuition but serves as the bedrock for comprehending the conduct of matter at the quantum stratum. Contemplating this transformative epoch in physics unveils the intrinsic nature of wave-particle duality as a foundational facet of the quantum milieu. Visionaries like Planck and Einstein, amongst other luminaries, charted a course toward a novel comprehension of nature, where particles and waves exist as dual facets of the same phenomenon, defying conventional cognitive paradigms. It appears that we are alluding to the progenitors of quantum mechanics, pioneers whose groundwork was later built upon by minds like Niels Bohr and Erwin Schrödinger. These trailblazers substantially enriched our grasp of the quantum universe. An eminent figure in this narrative is Max Planck, often hailed as the progenitor of quantum theory. In 1900, Planck introduced the notion of energy quantization, positing that energy manifests in discrete units or quanta. This concept marked a watershed moment, inaugurating the era of quantum theory. Albert Einstein, a key contributor, elucidated the photoelectric effect in 1905, proposing that light comprises discrete energy packets known as photons. This elucidation lent further credence to the concept of quantized energy, thereby fostering the evolution of quantum theory. Niels Bohr, in 1913, expanded on these early postulations by formulating the Bohr model of the atom. He advanced the notion that electrons orbit the nucleus at specific quantized energy levels, offering a framework that successfully explicated the spectral lines of hydrogen. Bohr's model became foundational in comprehending electron behavior within atoms. In 1926, Erwin Schrödinger introduced the eponymous equation, a pivotal formulation in quantum mechanics delineating the conduct of quantum entities as waves. This equation furnished a more exhaustive and overarching framework for deciphering particle behavior at the quantum echelon. The cumulative contributions of Planck, Einstein, Bohr, and Schrödinger, among others, played an instrumental role in sculpting the landscape of quantum mechanics, paving the way for the epochal discoveries that ensued. The double-slit experiment stands as a pivotal manifestation of the wave-particle duality, proffering profound insights into particle nature, particularly that of electrons. In this experimental setup, a stream of electrons is directed toward a barrier with two slits, behind which lies a screen recording the impact points of the electrons. When electrons are dispatched singularly towards the barrier, an interference pattern materializes on the screen, reminiscent of the patterns formed by light waves. This interference pattern intimates that electrons emulate wave-like attributes, exhibiting interference characteristics. However, the most intriguing facet arises when attempts are made to ascertain which slit the electrons traverse. Upon introducing an observational apparatus to track the electrons, the interference pattern dissolves, and electrons comport themselves more akin to particles, imprinting a simpler pattern on the screen. This phenomenon implies that the act of observation or measurement collapses the electron's wave function, compelling it to adopt a particle-like comportment rather than a wave-like one. This duality poses a challenge to classical perceptions of particle nature and underscores the profound influence of the observer on the conduct of quantum entities. The double-slit experiment has not solely been limited to electrons but has been extended to encompass other particles such as photons, showcasing a parallel wave-particle duality. This experiment remains an enduring cornerstone of quantum mechanics, shedding light on the intricate and captivating facets of the microscopic universe. Experiments in quantum physics, indeed, have been pushing the frontiers of our comprehension of the quantum realm. If we propel ourselves to the present, it is plausible that further strides have been made in this domain. Quantum entanglement persists as a captivating phenomenon, wherein particles become correlated in a manner such that the state of one particle instantaneously influences the state of another, irrespective of the spatial expanse between them. Scholars have been delving into the potential applications of entanglement in domains such as quantum computing and quantum communication. Recent strides in delayed choice experiments delve into measuring particles post-traversal through a bifurcated system. The tantalizing revelation lies in the retroactive influence, where opting to gauge a particle's position or path seemingly dictates its past behavior. These experiments defy classical causality intuition, challenging our perception of reality's nature. Within the quantum computing sphere, substantial strides may have unfolded, with researchers diligently constructing more resilient and scalable quantum computers. Quantum supremacy, the juncture at which a quantum computer outperforms classical counterparts, stands as an elusive goal pursued by researchers. Furthermore, ongoing inquiries may have unveiled novel phenomena or refined our comprehension of existing ones. The quantum enigma, marked by particles' bewildering behavior at the quantum scale, continually enthralls scientists, propelling them to probe the fundamental facets of reality. Staying abreast of the latest scientific literature or news becomes imperative due to the dynamic and swiftly evolving nature of the quantum physics field. Wave-particle duality, a cornerstone in quantum mechanics, elucidates particles' dual nature, exhibiting both wave-like and particle-like traits. Delving into the theoretical ramifications introduces myriad interpretations, with the Copenhagen interpretation prominently featured. According to the Copenhagen interpretation, particles simultaneously inhabit multiple states, forming a probability distribution until observation or measurement occurs. The act of observation precipitates the particle's collapse into a singular, definite state. This implies the pivotal role measurement plays in determining a particle's outcome. This interpretation poses profound philosophical queries about reality's essence and observation's role in shaping it. It intimates that observers wield substantial influence over a quantum system's outcome, challenging classical intuitions about a particle possessing a well-defined state independent of observation. As we delve deeper into quantum mechanics intricacies, the implications of wave-particle duality and interpretations like the Copenhagen interpretation persist as subjects of ongoing debate and inquiry in the realms of physics and philosophy. The many-worlds interpretation, a captivating concept in quantum mechanics, posits that every conceivable outcome of a quantum event materializes in a distinct, non-communicating universe branch. This conception implies the existence of an expansive multiverse, where each quantum event spawns a new reality. To simplify, envision a decision point or quantum event, like a particle's spin outcome. According to the many worlds interpretation, rather than the universe selecting one outcome, both possibilities unfold in separate reality branches. This continuous branching process gives rise to an ever-expanding tapestry of parallel universes, where all conceivable outcomes of quantum events unfold. This interpretation challenges the conventional notion of a solitary, deterministic reality, introducing the notion that all possible realities coexist in a vast and interconnected multiverse. While the many worlds interpretation is but one of numerous quantum mechanics interpretations, it ignites intriguing philosophical and scientific discussions about reality's nature. Beyond theoretical considerations, wave-particle duality bears practical applications, notably in quantum computing. Quantum computing leverages quantum particles' unique properties to deliver unparalleled computational prowess compared to classical counterparts. In the domain of classical computational systems, data undergoes processing through bits, existing exclusively in the binary states of 0 or 1. In contrast, quantum computing delves into the realm of quantum bits or qubits, capable of simultaneous existence in myriad states owing to the phenomenon of superposition. This distinctive trait empowers quantum computers to execute intricate calculations concurrently, resulting in a substantial acceleration of computational speed, particularly for specific problem categories. Moreover, quantum computers exploit another quantum intricacy called entanglement, where the status of one particle intricately ties to the condition of another, irrespective of vast spatial separations. This facilitates expeditious communication and exchange of information among qubits, thereby amplifying the capabilities of quantum computing. The potential transformative impact of quantum computers spans diverse domains, encompassing cryptography, optimization, and pharmaceutical exploration. They adeptly tackle challenges that classical computers find practically insurmountable within reasonable time frames. Despite being in nascent developmental stages, the pragmatic applications of the dualistic nature of waves and particles in quantum computing augur well for the future technological landscape. Venturing into the frontiers of scientific comprehension, researchers actively push the boundaries of knowledge to harness the enthralling phenomenon known as wave-particle duality. Grounded in quantum mechanics, this concept posits that particles, such as electrons, can manifest both wave-like and particle-like characteristics under specific conditions. Exploring wave-particle duality holds immense promise for unlocking innovations that currently reside only within the realm of our imagination. Researchers delve into the manipulation and utilization of this duality to forge groundbreaking technologies and applications. The prospective applications span diverse domains, encompassing quantum computing, communications, and sensing. Within the realm of quantum computing, capitalizing on wave-particle duality could birth more potent and efficient quantum processors. These processors, with the potential to revolutionize computation, engage in complex calculations at speeds surpassing the capacities of classical computers. In the domain of communications, mastering wave-particle duality may usher in the era of secure quantum communication systems. Quantum key distribution, a technology grounded in the principles of quantum mechanics, holds the promise of offering unparalleled security levels in the transmission of sensitive information. Furthermore, researchers probe into how wave-particle duality can augment sensing technologies. By harnessing the distinctive properties of particles in their wave-like states, sensors may achieve unprecedented precision in detecting various physical quantities, ranging from gravitational waves to magnetic fields. As our comprehension of wave-particle duality deepens, the potential for transformative innovations continues to burgeon. While these possibilities may appear as mere aspirations today, ongoing research gradually transmutes them into tangible realities, paving the way for a future where the enigmatic principles of quantum mechanics propel technological advancements beyond our present understanding. Explore the mesmerizing realm of wave-particle duality. If delving into the intricacies of quantum mechanics has left your curiosity ignited, ensure to show your enthusiasm by liking, sharing, and subscribing. Don't miss out on future mind-expanding journeys into the marvels of science. Hit that notification bell to stay abreast. As we part ways for now, fellow seekers of knowledge, persist in questioning and unveiling new discoveries. This marks my departure from the realm of scientific wonders. Stay inquisitive.